Okay, so we will continue about UVb spectroscopy or absorption. So we're going to discuss about the application of the UVBs. So UVBs is useful if you have, let's say, a single component analysis. But as we all know, most of the samples are made up of different components. So common problems arises when you have, let's say, mixture. Okay, so when you have a mixture, your blank samples often contain multiple absorbing species. So it's not only the target analyte that absorb the light. Okay, so some other materials that are present there can absorb the light. So what happened there is we have to take into consideration that the sum or the absorbance that we get, that is the sum of all the individual absorbances. So we cannot take into consideration that when we have the absorbance, it's just coming from the target analyte, especially if you have a complex sample in conditions where you have what we call the mixture. So in that case, you just have to take into consideration that the absorbance is not coming only from one source. It's the sum of all the components that are present. Okay, so substances in both the blank and the sample which absorb can be blanked out in both double and single beam spectrometer. So if you're going to look at the example here, so as you could see here, okay, there's a sample H that you have here. So it's one of the thing over here. Now the sample H that you have there, okay, is equal if you model all the individual component that is present there. So you can find the model there that the sample H that you have there is just the summary or the sum, the total absorbance of all the component that you have where you can make here an acetone, which usually has this absorbance. Okay, and then you have the benzene, which is usually this one, the green. And then you have the chloroform, which is just that one. So if you're going to look at the summary here, the sum here, so this is what happened if you add this, this, and this one. Okay, so if you have this thing, you have to consideration to take into consideration that there are other constituent or components that distribute or contribute to the sample absorbance. Okay, so that's just one common problem that we can have, and we can also take a look that if the blank absorbance is high, so the transmission going in will decrease too much and the response will be slow and the result would be inaccurate. Okay, so if we're going to look at the wavelength scan of the substance, okay, we can have an ideal absorbance like this, but if there's a large blank absorbance, that thing will become like this one. So as you could see from a narrow peak, you have what we call a broader peak here. Now the broader peak here is something to do with the large blank absorbance. Now to solve this, okay, or if the blank absorbance is so high, these are the things that you can do. You can dilute the sample, okay. So diluting the sample will minimize the large blank absorbance. You use a different wavelength where the analyte absorbs more relative to the interference. So when you use a specific wavelength, okay, it just target your analyte, okay, compared to the interference. Or you can use a different method of separation, removing, okay, the blank or the constituent that cause this large blank absorbance. Okay, so that's one of the common problem if you have what we call the mixture. Okay, so if you're going to use chromatography with UV pieces, the thing most likely you will get that thing. And if ever there are other samples, there's just another peak that you have. And all you need to do is determine the retention time of the target analyte that you're looking for. Now, another thing that we have to look at is the so-called instrumental deviation from the Beer's law. Okay, so we talk about stray light and the presence of this what we call polychromatic light. Okay, since you're using here more than a single wavelength. So since all instruments, they have a finite bandpass, a range of the wavelengths are sent to the sample. And we could say the molar absorptivity there may be different for each what we call absorbance. So this can be observed in terms of the wavelength. Okay, so if you have a bandpass here, so this bandpass may just catch this area, and this bandpass may just catch this area. Okay, so if that's the case, you could see that there are what we call different wavelengths here. Okay, now if you're going to compare the bandpass that you have there, so ideally you want it to be like this, where you have the B and the A, but unfortunately, if it's just okay, no, if you have what we call the band, only the band A, which is this one, but if you included, okay, or you just look at the what we call band B, so you might have it like this, because what you have here, the band B is not usually the lambda max. Okay, so in this case, we could say the molar absorptivity here is different from the molar absorptivity here, and it's going to give you a different what we call Beer's law, which is a deviation from this what we call concentrate at high concentration. Okay, so we can look at this deviation from Beer's law. Let's say we have two wavelengths of light entering the sample. So one at 254 and one at 255. So you could see the difference here. One is 2 times in terms of molar absorptivity. Okay, so if we're going to let the light that goes in equals to 1 at both absorbance, okay, we can see what happens to the Beer's law plot as the concentration increases. So the way that we're going to look at this, the absorbance, as I told you, this is just the absorbance of both the contributing species, okay, or the light that you get there. So as you could see here, one coming from 254 and one coming from 255. Okay, so if we're going to look at the individual wavelength, so we can have this absorbance as 254 is just equals to the molar absorptivity times the length of the cuvette times the concentration. Okay, and then we can going to look at the what we call the lag of the absorbance, no, not absorbance, the transmission that goes in and transmissions that goes out. So we can get what we call the ratio that we have here. Okay, so looking at this, so absorbance is equals to lag of initial transmission over the outer transmission or transmission that go out total. So this is just lag of this over this one. So the one that enters over the one that what we call transmitted. Okay, so from this, what happened here, okay, is the absorbance is just equals, okay, to the lag of the transmitted light over the light that was what we call the light that was enter your sample over the light that goes out. Okay, and you have to take into consideration the contribution from this. And if we go further here, okay, putting the amount that we have, so since the both has a concentration equals to 1, it says there, or not the transmittance equals to 1, which is just 100% transmission. So if we're going to look at this, so these are the value that we can get. So the A that is actual versus the A that is what we could expected. And if we're going to look at this, okay, you could see here a negative deviation. So that means in the actual value, okay, it didn't follow the Beer's law. So if it's expected here, so you could see at lower concentration, it's still close, but as the concentration, okay, becomes higher, the deviation that you have there also increases. Okay, so we could say the results are the same for more wavelengths of light, and the situation is worse for greater differences in molar absorptivity. So the side of absorption peak, the broad band pass. So this is what we call one deviation that you have for the Beer's law, especially it happens at higher concentration. So what you need to do is you always need to do the calibration curve. And you do this to determine the limitation of your Beer's law. You cannot assume linearity outside the range of the linearity curve. So based on this, I think we can you can just be said that, oh, maybe it's just here to this one, because after this it's already so far from the expected absorbance. So maybe from here you could say, oh, we can just use this until here. If you go over that concentration, the Beer's law is not already, we could say, observed. Okay, and this is just what we call instrumental deviation. Okay, so it has something to do with the response of your what we call instrument, the presence of the stray light or the so-called polychromatic light. Okay, now another deviation that you can have from Beer's law is what we call chemical in nature. Usually, the molar absorptivity changes to solutions in more than constant in solutions more concentrated than 0.01. So what does it mean? This is the max concentration that you should use. Okay, and the reasons for these are many. They could be due to molecular interaction, and at concentration higher than 0.01, the Beer's law assumes species are independent. Okay. And then electrolytes may also cause this problem. And the molar absorptivity is also affected by the index of refraction, because I think what happened here is you have more compounds or component that is already present. So whatever interaction that they have, okay, may affect the absorption, or we could say the signal that they can have. Okay. Now, you can also have to do it with the association, dissociation, precipitation, or reaction of the analyte. Okay? Usually, the concentration in Beer's law is the concentration of the absorbing species. Okay? So, commonly used the analytical concentration or the concentration of all forms of the species. So, for instance, in phenolphthalein, we know phenolphthalein is affected by what? The pH, right? Because phenolphthalein at different pH, they have different form. So we could say the protonated phenolphthalein is colored, so it has an absorbance at 600 nanometer. But at higher pH, it is colorless, so it will not absorb anything. Okay. So what happened there, if you buffer the solution, we could say pH is constant, and the concentration of the protonated phenolphthalein is related to the absorbance. Now, this is true only if it's what we call buffered. Now, what happened if it's not buffered? If it's not buffered, the equilibrium will shift depending on the total analyte concentration. So what will be favored is depending, okay, on this concentration and this concentration. So if the Ka is equal to 10 to the negative 4, okay, you will have different ratio here. And depending on the concentration there of your indicator, so you will know, okay, that the actual absorbance will deviate from the expected one. Okay, so with a concentration of what we call, or we would see concentrations of this one, so they found out that the ratio that they have is this 0.0924. If you increase the concentration there, that one also increased because, as you could see, H indicator is in the numerator compared to the protonated indicator. Okay, so here you could see an apparent deviation. And this can be accounted by the chemical equilibrium. So we know K is just equals to the product over the indicator. So if you're going to look at this, so if you have an expected absorbance here, a different concentration of what we call the indicator or the buffered, if you have an unbuffered one, it will have a negative deviation. Okay? But if the unbuffered solution, okay, equilibrium masses will shift depending on this, what we call total analyte concentration. But what happened is we always have this so-called isobestic point. Ano yung ibig sabihin ng isobestic? Is that the first time for you to hear the term?
Same po yung absorbance.
Okay. So when you have an isobestic point, what happened is it's in a specific wavelength, the wave number or frequency at which the total absorbance of the sample doesn't change. Okay. And usually they use the isobestic point, especially for the one that change composition, let's say a different pH. Okay, so for instance here, the isobestic point that you have is this one here. Okay, so as you could see, B is what? Okay, so your B here is the dissociated one. The A is the one that is what we call the undissociated one. So what happened? Okay, so there will come a time that it shift coming from here, going to here. Now at isobestic point, they said the absorbance is just equals to the molar absorptivity times B times the concentration of your protonated and deprotonated form. So usually makikita mo yan yung tataas. I think usually ganun. Tapos mangyayari tataas. Tapos pag tumaas to, bababa yung nandito. So usually in each species that what we call solvatochromic, you will always have an isobestic point, okay, wherein the absorbance doesn't change. And that's your guide for you to determine the concentration of the species that you have there. Okay? So yan lang yung problem no associated dito. And this usually involve either the one that depends on the pH or the one that changes in its absorbance depending on the polarity of the solvent. Okay? So usually ang nangyari kapag more polar nagre-redshift, kapag less polar nag-blue shift or the other way around. Okay? Now, another thing that we can get is non-constant B. So as much as possible, okay, we want them to be what? Constant yung length ng ano mo, yung path length. Okay? So they said it is worse for round cuvettes. But magiging worse lang yung pag yung round cuvette mo ay ganito. Because they're not constant. But usually when we have a round cuvettes, yung round cubette namin dito, inaano namin. So ito yung parang path length niya. So it's still the same. Okay? So as much as possible, you want to use what we call the parallel cubette. Ito parang ano to eh. Parang pag nagiinuman kayo nilalagay tapos sa maliit. So the path length in B2 is much higher than the path length in B1. And that's not good. As much as possible, you want it to be what we call the same. So that all throughout, okay, you could say that the light transmitted, okay, is proportional at any what we call angle or side here of your cubette to the light that was, so the light that goes in, okay, is the same as the light goes out. Kasi mangyari kapag dito sa taas, ito lang yung amount na transmit. Kapag dito naman mas liit or shorter yung wavelength, mas marami yung na-transmit na light compared dito. Kasi mas wider yung length nito, so mas marami yung na-absorb compared to the one that you have here. But you seldom see that because usually ito, sabi ko nga sa inyo, yung round cubettes, usually we do it going here. But some, I don't know for what reason, pag ganito yung ginagawa nila yung pagpasok ng light. In that case, it's not what we call uniform. So that's the third problem, okay? Doon sa common problem in absorption. So this is just talking about A equals to this. So ang affected dito is this one. Now the next one, I think this is true, not only for spectroscopy, I mean absorption, but in all spectroscopy method, yung tinatawag natin instrumental noise. Okay? So when we're talking about noise, this is the short-term baseline fluctuations which decrease the precision of the analysis. And when you have this noise, usually you cannot measure the absorbance precisely. So I think this is one reason why when you turn on the instrument, what do we do? Do you read it right away? Usually you warm it for what? At least 10 minutes. Okay, because you want to make sure that you lessen the noise. Okay, because if you don't do it, the fluctuation comes in, and especially there in the country, di ba, pag brown out. So yung ano talagang mag-aano yun. Dito nga, yung movement lang ng elevator, it can affect noise. When you're working in Raman, the noise that we have is the cosmic rays. And we don't have any choice on that. Okay? So the only thing that we can do if we have noise is maybe to get more reading. Okay? Because I told you, there are what we call various sources of noise, each cause some uncertainty in the absorbance measurement and can be treated as individual standard deviation. Okay? So usually makikita mo naman yung effect ng noise. Let's say in first reading, meron kang nakitang ganyan. So in the second reading, ganun pa rin. Pero in the third reading, so you could say that's part of the noise. So you just have to do multiple reading. So 0% transmission noise, so noise when the light beam is blank. Okay, it's seldom important and typically it's just around 0.01% of the transmission. And then you have the readout precision, especially if you have a meter. So typically it's 0.5% transmission, which is 1 to 3% error in the concentration. Now, meron din tayo tinatawag na shot noise. So shot noise happen when the electron transfers across the junction. So like the space between the cathode and anode in your photon multiplier tube. And the shot noise causes random fluctuation in currents as individual electron arrive at random time. Okay? And shot noise would increases with increased current, especially bad if you have above 95% transmission. Now, another noise that you have is the so-called flicker noise. So this is the noise coming from the lamp due to intensity change. Okay, and this is usually important at high transmittance. So, di ba, I don't know, even in an ordinary light there, when you see sometimes the electricity fluctuate, you see the changes in the lamp. Okay, yung parang lalabo, tapos biglang ano. So that's so-called a flicker noise that happen. Okay, and it's usually, we could say, common doon sa light source mo. Okay, we could say flicker noise, type of electronic noise. Okay, ang tawag nila dyan is pink noise. And they said it's believed to be caused by the charge carriers that are randomly trapped and released between the interfaces of two materials. Okay? And then you also have to take into consideration yung tinatawag nating self-positioning as uncertainty. It's not really a noise, but it affects the precision. And then this can also be due with minor imperfection, the presence of the scratch or dirt in your cuvette. It can change the percentage transmission or transmittance. And it can be the major cause of imprecision. Okay, so some of the things that you can have here, category 1, so characterized by this K1, so you have a limited readout solution. So likely to be important in inexpensive photometers and spectrometers having small meter scales. And then you have this heat detector Johnson noise. So this is applicable in IR and near IR photometers and photometers. And then you have the dark current and the amplifier noise. So this is the regions where the source intensity and detector are usually low. Now, another case that you have here, okay, has something to do with the photon detector shot noise. So here, it's likely to be important in high quality UVb spectrophotometer. And then in case 3, the self-positioning uncertainty that happens also in UVb and IR. And the source flicker, okay, yung flicker noise, which happens in inexpensive photometers and spectrometers. And if we're going to take into consideration this different noise, okay, so taken together, these noise sources indicate that intermediate absorbance and transmittance regions should be used. So at low percent transmission or 0% transmission, the noise and the readout precision are important. Okay, and at high percent transmission, the shot and the flicker noise are what we call large. And as much as possible, to minimize this noise, we need to keep the absorbance between 0.1 to 1.5. Although we said we want the max to be around 1. So this 0.1 to 1.5, that's equivalent to 80 to 3% transmittance. Now, these are just the common problems that we have in using UVbs. Now, we like to look on where do we apply these UVbs. Okay. So, usually we apply it to determine the molar absorptivities in UVb's range. And once we know the molar absorptivity, we can use it as a quantitative method. Okay, so for instance, you can have a molar absorptivity of 8.7 times 10 to the 19, okay, times the power times the absorbance. So we could say this is not the power, the probability, that's the transition probability times the cross-section target area of the target molecule. So that's the formula that you get for the molar absorptivity. So Your p-value there would range from 0.1 to 1 for likely transition. And then the cross-section that we have here, that's the thing. So for typical organic, the cross-section area that you have is 10 to the negative 15, okay, giving you a molar absorptivity of 10 to the 4 to 10 to the 5. Now, what is the relationship of absorbance with molar absorptivity? Do you want your molar absorptivity to be high or low? If you're going to look at this. So based on this one, this is directly proportional. So if this is high, so that means even at lower concentration, you can detect the absorbance. If this is low, the absorbance will be low. Okay. So as much as possible, you want to be your molar absorptivity to be higher than 10 to the 3. If it's less than 10 to the 3, you have low intensity. Okay. Then if you have a low intensity, that means the p-value that you have there, the transition probability is less than 0.01. So here are just some of the molar absorptivity at a certain wavelength of this, what we call different compound. So you have here toluene at 206 nanometer, okay, around 7,000 molar absorptivity. Compare it with the cyclohexane hex to enon, which is around 10,300. Okay. Now, this is useful also if you have multiple chromophore. Okay, so chromophore is the one responsible for the absorbance. So sometimes your given compound has multiple chromophore. The one that I worked on my dissertation, tetracycline, I have 3 chromophores there. And what I do is I just look at the what we call, if I'm not mistaken, 230, 260, and 360. So those are the wavelengths that I look for. So what does it mean? It absorbs as those wavelengths. Okay. So for compounds with multiple chromophores, if greater than one single bond apart, your molar absorptivity are additive, okay, and the wavelength is constant. So for instance, this, natawag natin dito, 1, 2, 3, 4, 5. So this is what? 1 hexene or pentene. So it has a lambda max at 184, and the molar absorptivity at lambda max is 10,000. Now, if you have this one, 1, 2, 3, 4, 5, 6. So this is 1,5 dihexene. Tama ba ako? Anyway, we all know it like this. 1, 2, 3, 4, 5, 6. Oops, should be like that. So the lambda max at 185 is this one. Okay. Now, if you have this one, so this is a conjugated one. So what happened? If you have a conjugated one, your lambda max would redshift. It goes to higher wavelength. So if we're going to look at the example that we have here, so you could see this sample has how many chromophore? So you have 1, 2, 3 chromophore. The violet one, you have 1 here, you have 1 here, you have 1 here, you have 1. That's 4 chromophore. And then this one, you have 1, 2, 3, 4, and maybe this one, the 5 one. And they are useful, okay, to determine their absorbance, or we could say the concentration, knowing they're what we call absorbance. But usually, which chromophore you're going to use? So if you have multiple chromophore, which do you think is the one that you're going to use for practical purpose? Pag may nagtanong ako sa inyong ganyan, aling bond ang gagamitin nyo? You're going to use the one that has
Yung highest pa rin, sir.
the highest signal. Because when you have the highest signal, you just need a small, low concentration to detect it. Because sometimes what will happen, if you're going to use a lower one, ang mangyari yan, cut off na to. Yung hindi mo na makikita yung max niya kasi na-cut off na siya. So usually, for practical purpose, you use the highest one. Okay. So that's one way to use these UVBs in terms of this molar absorptivity. Okay. So it used this so-called conjugated thing. Now, another thing that we could do is look at the absorbing species. So absorbance is just electronic transitions, and this involves both the organic compounds and the inorganic compounds and the complexes. Okay? So ano yung mga inorganic compounds na meron tayo? We could include the metals. So if we're going to look at the basic process, so you have your sample, apply it with light. So there's an electronic transition. So this sample that was applied with light, okay, it can give up the material in ano ba tawag natin? Excited and ground state. Okay, go back to the ground state and heat. So that's in the form of fluorescence light or phosphorescence. Or we could have a new species that produce a photochemical reaction. And if you're going to look at this, you can get the so-called lifetime. Okay. How long they exhibit that one. So the excited state that you have here is generally short and heat produced, not generally measurable. Okay. Thus you get minimal disturbance of the system, assuming no photochemical reaction. But if you're going to look at the absorbance that occurs with the bonding electrons, so you could see that the wavelength requires differs with the type of the bonding electron. The UVb's absorber gives some information on bonding electrons, which is the functional group in the compound. And this is applicable mostly for the organic compounds. Okay. Because if you have these organic compounds, their spectra are usually complex. You have the electronic and vibration transition superimposed. You could see here an absorption bonds that are usually broad. So just try to look at this. So this is what the beta carotene, and this is the aspirin, the acetone, and the caffeine. Okay. Now you can do a detailed theoretical analysis. Okay. But this is not possible for quantitative one, but semi-quantitative or qualitative analysis of type of bond is possible. Okay. And the effect of the solvent and molecular details complicate the comparison. So what does it mean? At different solvent, you're going to have different spectra. So some of them might move to that one, or some of them might move on this one, depending on the what we call solvent. So this is applicable to the tinatawag na solvatochromic materials. They just exhibit solvatochroism. Solvatochroism. So this is dependent on what we call the polarity of your solvent. Okay, so there's a reversible change of the absorption or emission spectrum of the material that is induced by the action of the solvent. And it's a very good field. So yung iba, mag-ano lang na sila ng paper by just looking at what we call. So what happened to the spectra if you use different alcohol? So I remember I have one. I have this derivative of tetracycline, which is anhydrotetracycline. So I started from C1 to C8 of the alcohol. So you have methanol, ethanol, propanol, butanol, pentanol, hexanol, heptanol, until what we call octanol. And I see that it's shifting depending on the polarity of the solvent. Okay, but this is only applicable if you only have that compound there. So it will be complicated if it's what we call the mixture. Now, single bonds, usually they use what? Higher energy for instruments. So 185 nanometer is usually an ultraviolet, vacuum ultraviolet. So most compounds of atmosphere absorb this range, so it's difficult to work with, damaging to the eye. So usually concerned with functional group with relatively low excitation rates of between 190 and 850 nanometer. So yan yung UVb region. Now you have this type of electronic transition. Okay, so you have the sigma, pi, and electrons. So if you have the sigma, so that's a single bond electron. So you have the sigma to sigma star. I think this is Chem or inorganic chemistry. Okay, so usually the sigma star is the one that has a higher energy level. Okay, one is the bonding and the other one is the anti-bonding orbital. And then you can also have this pi, so the pi to pi star transition. Okay, and then the N, this is just the non-bonding electrons, and they don't take part in any bonds. They're neutral energy. So if you're going to have a formaldehyde, so based on what you have here, okay, you have what? Whenever you have a double bond, what do you have? So this is a sigma, this is a sigma. So you have a sigma here and a pi. So if you're going to look at the electronic transitions that you have for a formaldehyde, you have a sigma and a pi interaction. Okay, and since you also have a lone pair, so you also have the N, the non-bonding interaction. Now this is very helpful, okay, because based on this interaction, you can see changes in the absorption. So if you have a sigma to sigma star transition, okay, it happens usually at vacuum UV. Why? Because they're more stable, so you need higher energy. Look at the amount of energy that you need here. Does that make sense? So you're going to need shorter wavelength. Okay, and then you also have an N to sigma transition. So this happens in saturated compounds with non-bonding electrons. So the absorbance, the wavelength will be around 150 to 250, and the molar absorptivity is at the most 3000, which is not really strong. Okay, so if you're going to look at this, this is what? Non-bonding to sigma. So this is just around here. And then you have the N to phi star. So this is just here, the N. Okay, so I think this is the weakest among them. Okay, it requires unsaturated functional group, usually the double bonds. Okay, and it's in their energy good range for the UVBs. So the wavelength is around 200 to 700 nanometer. Okay, now if it's N to pi, and this also include the pi to pi star here. Okay, so if it's N to pi, it's just 10 to 100 molar absorptivity, which is quite low. And if it's pi to pi star, it's around 1,000 to 10,000, which is much better. And if we're going to look at some of the common chromophores that we have here, we can see the type of transition that we have. Alkene would be a pi to pi star because of the presence of the double bond. Now, alkyne also have a double bond. So you can expect there a pi to pi star transition. Carbonyl, whenever you have a double bond, you expect a pi, what we call pi star here, at least in the system that we have here. Carbonyl with the solvent in N-hexane, so you could see the pi, N to pi star in both of them, and N to sigma star. Okay, so these are the different what we call transitions. So all you have here are what? Organic compound, and we're going to look at some of the other common thing here based on the functional group. So this is the transition that we have. So this is really useful for this so-called organic compound. Now, we didn't include here, okay, the inorganic stuff, because we said we can use also this for inorganic stuff. So the inorganic stuff would involve what? The metal. So this is where we have what? The D and the F electrons, because that's the one that contains the transition metal ion. So we have the lanthanide and actinide series. So you have an electronic transition of the 4F and 5F electrons. And then this is generally sharp, well-defined bonds, not affected by associated ligand. And the first and the second transition metal series that we have, there's an electronic transition of 3D and 4D electrons. Usually they're broad peaks. I'm not sure if you have taken the advanced inorganic chemistry. There's this crystal field theory that was discussed there. Okay. So here, these are the different what? D orbitals. You still remember S, P, D, F, right? So usually I call it, this is what? The spherical or sphere. And then I call this the peanut, because a p orbital is really like a peanut, right? And then the D here, I call it the double peanut. And then the F, I call it the flower. It's just describing the shape that they have. Okay, usually you do it in Gen Chem class, SPDF, to simplify it. But you know, S orbital, P orbital, D orbital, F orbital. I just refer this to shape. Okay, I just read it from somewhere else, not really my original idea. But you see the peanut, there is just the P orbital are like this or like that or like that. It's shaped like a peanut. And if you have a D, it's a double peanut that you have seen here. So in the crystal field theory, in the absence of the external field, the d orbitals are identical. And the energies of the d orbitals in solutions are not identical. So the absorption involves the electronic transition between the d orbitals. And in complex, or orbitals increase in energy where orbitals along bonding axis are stabilized. So why do you think some metals are colored? Copper. What's the color of copper 2+?
Blue.
Okay, so it's blue. So that means it can absorb something. Now, if you're going to look at the absorbance, this has something to do with D, changes in the D thing. Okay, so if you're going to look at the magnitude of these what we call changes, it depends on the charge on the metal ion, the position in the periodic table, and then the ligand field strength. So the ligand field strength that you have there, iodide is the weakest, cyanide is the strongest. So if you're going to look at the increase in the changes here with increasing field strength, so the wavelength decreases. Okay, so depending on the shape of the complex, so this is the difference that you have. If you have the octahedral, the tetrahedral, and the square planar. So all of them involves the Dre transition. Now this is useful if you have complex. I think Emil, nag 120.1 ka ba?
Yes po, sir.
Did they still synthesize the complex with different color? I didn't thought 120.1, but I always know the experiment. There's colorful.
Apo, sir, yung cobalt tsaka molybdenum complex po. Yes po.
So the explanation that they have there is this one. Depending on the shape that they have, same metal, but different complex, they will give you different color. Okay, and it has something to do with the charge transfer complexes. And it's really useful. A lot of them develop a method. Let's say if you want to determine metal, by complexing it, okay, with organic substance, like the iron penanthroline complex is very, we could say, useful. Dapat nandito si Loren eh. Ito yung parang thesis niya eh. The zinc DMG. I think dimethyl glyoxime is another one. So instead of just monitoring for a metal, by complexing the metal with an organic compound, you can have a much more sensitive method. Okay? So it's important analytically because of this. So tumataas yung sensitivity niya. Remember, this affect your Beer's law. So if this is high, your absorbance and law also high, so you can get the absorbance even at low concentration. Now, the absorption of radiation here involves the transfer of electron from the donor to orbital associated with the acceptor. And the excited state is a product of the pseudo-redox process. So many inorganic complexes of electron donor, usually organic, and electron acceptor, usually the metal. So ang ano nga yung iron thiocyanate at saka yung iron penanthroline. So you can detect Fe3+ if you complex it with SCN- compared to Fe3+ lang. Ano ba yung Fe3+? Ano yung color niya? Usually, ano yan eh?
Yellow.
Yellowish. But you can detect its presence more if you react it with thiocyanate because it's going to produce a deep red color. So this is already a complex. Oh, this is the yung tinatawag natin bloody red solution. Okay. So the same thing if you have this penanthroline. So napaka ano yung tong field na to. Okay. And they were able to have a lot of patent out of this one. So once they see, oh, we can get a patent out of this, and that's the basis that they have to measure metal content in our body. So all you need to do is find a certain wavelength and determine the molar absorptivity. So once you know the wavelength, once you know the molar absorptivity, all you need is when you get the absorbance, you can determine the concentration. Madali lang naman yung molar absorptivity eh. Okay? All you need to do is what? How do you get molar absorptivity of a compound? Kaya nyo? Paano nyo i-determine yung molar absorptivity niyan? Sige nga.
Galing po sa slope ng calib curve.
Okay? So all you need to do is make a calibration curve. Okay? So you have there A and C. So ano man yung ano nito? So pag inano mo yan, concentration absorbance. So yung slope niya, yun yung molar absorptivity. Usually, ang una mong gagawin, scan mo muna. Tapos, kung saan yung mataas yung lambda max niya. So, yun yung gagamitin mo. At then, prepare the different concentration. And then you plot it, and then you get the, what we call slope. Okay? So, that's we could say, another applications that we have by looking at the transition, the absorption that occurs with the bonding electrons. And it's applicable for both organic and inorganic species. Now, the next application that we have is qualitative method. But this is not really good, okay? It's limited because you don't have good peaks. And it's an ambiguous identification, not usually possible. Kasi nga, as I told you, okay, some of them are solvatochromic. Solvent can affect the position and shape of the curve. Polar solvent broadens out peaks and eliminate the fine structure. Okay, so here, in this example here, you could see the loss of fine structure for acetaldehyde when transferred to solvent from gas phase. Iba usually yung gas kaysa doon sa solvent. Sa absorbance. And then here, so kapag alcohol siya, medyo narrow yung peak niya, but when you have what we call water, then it is broad. Okay? Now, some explanation that they have here is the difference in the environment. So it's possible that this thing, at this what we call condition, your sample interact with water compared to this one. Now, as I've told you, the solvent can affect the position and shape of the curve. So polar solvent usually broad, okay? And it can eliminate the structure. So if you have vapor, so ganyan lang siya. Puro, sabi namin dito, noise. But if you put a solvent on it, it becomes broadened. So this is non-polar. But if you have the polar, you could see, okay, it just broadened. So this is the 1245 tetrasin. A solvent polarity increases. So as you could see here, okay, so we could say that it has different chromophore. Or this one is responsible for some of the element that you have in this what we call compound. Okay, tetrasin. Tetrasin is what? Is it a dye? Ano yung tetrasin na yan? So usually it's just what? N? But it is 124 1245 tetrasin. Okay, so it's different when you have what we call an aqueous one. And you can do a calculation of this in Gaussian to get the absorbance. Do you do anything sa PChem nyo? Did Dr. Manalo do some computational stuff in your PChem?
Meron, sir, pero parang output na namin. Like, it's up to us to do the computations. Pero like, walang computation using software sa klase mismo.
Hindi niya kayo binigyan ng ano, copy? Siguro bigyan ko kayo.
Hindi.
No, I have
Ano, games
reinstaller.
ata yung papagamit sa amin.
Games. Games I think is free. But I gave him a copy of the Gaussian. Then you can do what we call compare kung ano yung, although I don't usually use it, but you can have a theoretical absorbance in the calculation. I use Gaussian only for my vibrational frequency. Okay, but that's a good one. So you can see that if you put a solvent, it's really different than just the vapor. Now, another thing that you have is the solvent. Okay, so some of the solvent usually they can be absorbed in the UVb spectrum. So water, yung lower limit niya is 180 nanometer, which is good. But acetone, so if you're going to look, I think I have an example here of the absorbance of acetone. So as you could see here, you cannot use acetone here unless what? How do you solve the problem of the solvent? Anyone?
Some other wavelength yung gagamitin mo, sir.
Some other wavelength, ano pa?
Blank.
Blank. So you set this as a blank or C0 mo. So everything that is blank. Okay. So that's one way to get away with the problem with respect to the solvent. Okay. Now, another thing that we can look at is we can obtain some functional group information from certain types of compounds. Okay. So this experiment that you see here, we do this here in undergrad. Pero ang ginagamit namin is naphthalene, tapos yung benzene, tapos I think anthracene. So the way that we look at this, the more rings that you have, okay, the longer wavelength that you can monitor it. So weak band at 280 to 90 nanometer that is shifted to shorter wavelengths with an increase in polarity implies a carbonyl group. So acetone is an example of a carbonyl group. So if you put acetone in hexane, it's 279. But if you put it in water, it's going to blue shift. So I think this is the example that you have here. Okay, so this is the one in heptane, and this is the one in water. And if you could see here, mas broaden nga yung ano dito kaysa dito. Kasi polar to kaysa dito na non-polar. So solvent effects due to stabilization or destabilization of ground or excited state is just due to the change in the energy gap. So since most transition results in an excited state that is more polar than the what we call ground state. So 260 nanometer with some fine structure implies that you have an aromatic. Sa protein, ano yung ginagamit nila to determine the protein content? Diba usually it's either 260 or 280. Why? Bakit 280 nanometer para sa protein determination? Anong meron sa 280? Nandiyan yung aromatic ring. Phenylalanine, tyrosine. Okay? And that's the one that can give you the absorbance. Of course, depending on the protein, iba yung molar absorptivity niya. But usually, it's a 280 that you can get the maximum signal, yung lambda max. Okay, so more complex ring shifts to higher wavelengths or redshift similar to the conjugated alkenes. Now, the UV spectral nomenclature, so itong redshift, tawag natin is bathochromic. Kapag blue shift, tawag natin is hypsochromic. Kapag going up, hyperchromic, going down, hypochromic. Now, aside from qualitative analysis, I think the main application of absorbance is in quantitative analysis using the Beer's law. Okay, so widely used for the quantitative analysis characterization. So it can be used both in the organic and inorganic compound. And the limit of detection that they have is 10 to the -4 to 10 to the -5, although they were able to lower it 10 to the -6 to 10 to the -7 molar. Moderate to high selectivity, and it's typically accurate, 1 to 3%. Okay, and you can get around 0.1%. And this is the most important one. It's easy to perform and it's a little bit cheap. Spectronic 20 can do everything. I think after the balance, this is the most important instrument that you need in the lab. Okay, and you can do a lot of analysis. So the strategy here, you look at the absorbing species, so you detect both the organic and inorganic compound containing any of these species. So we have the absorption characteristic here, so you can look at the lambda max. Once you have the lambda max, you can get the molar absorptivity. So as I've told you, using this, all you need to do is, you know this, you get this, and you can determine the concentration of your sample. As easy as that. Okay. But you also have to take into consideration that some of them can be still used in those non-absorbing species. But how do you do this? You're going to react it with something so that it can form a product that can absorb. Okay, so you react it with a reagent that forms colored product. Can also use for absorbing species to lower detection limit. So items to consider: the wavelength, the pH, the temperature, and the ionic strength. So you have to optimize this condition. And the way you do, you prepare the standard curve, you match the standards and sample as much as possible. So for instance, okay, you Fe3 plus, although it's yellow, but sometimes it's usually colorless. So what you're going to do to make it into a color product, you react it with apotransferrin, which is also colorless. And the way that they do is they form a complex red. Okay. Now you can also use this for binding. So apotransferrin is what? That's also a protein. So the way that they do to determine the presence of the apotransferrin is you add different amount of Fe in terms of different volume. So it will increase until such time, okay, that it's not linear anymore. So when that happens, that means all the protein has already bound to the Fe3 plus. So there's no more increase in the absorbance. And another thing that you can do, I'm not going to do any calculation here, is the standard addition method. So you're going to use it for those that contains sample that gives matrix effect. Okay, so used for analyzing a complex matrix where interferences in the UVb for the analyte will occur, like blood, sediment, human serum, and other things. So the way that you're going to do is you can do different amount or different volumetric plus here, and then you add several aliquots of the unknown sample, or you can only do one. Okay, one that contains your sample and one that you contains your sample and an added standard of known concentration. So you can do it this way or the single point standard addition. So you add a variable volume of the standard of the solution here, okay, to each aliquot. So the way that you're going to do is you're just doing like a calibration curve, but you can just use, let's say, two of them. So one, you add with the standard of known concentration, and the other one is just your sample. And you add the sample also there with the standard of known concentration. So you can do this one, calibration curve, and you just extend here to determine the concentration of your unknown. Or you can just compare it, okay, with single point standard addition, which I'm not going to do here. So the way that you're going to calculate the concentration is just like this. So this is the one using the calibration curve, but I have told you, you can do a single point. Natakal ba to sa 32? Standard addition?
Sir, sa 137 po.
Sa 137. Oo nga. Yung first chapter namin to. Yep. So you can either do the single point standard addition or this one that has the calibration curve. And then you can also use this, what we call two-component analysis of UVbs. So you have here two different wavelengths with different molar absorptivity. So the way that you're going to do it, this is your sample that contains both N and M. So all you need to do is determine how much M and N that you have based on the knowledge that you have. So this is what we call simultaneous equation. So you have A1 here, okay, equals to molar absorptivity of N times path length times the concentration of N plus molar absorptivity of N plus times path length times concentration of N. So the second absorbance that you have here, okay, so this is the one here, and this is the one here. And the way that you're going to do it is you just combine this data to determine the concentration here of both M and N, and also here, M and N. And last that you're going to have here is the photometric titration. So it's similar to what you did here, transferrin reacting with a non-absorbing species. So you require the analyte or the titrant or the titration product absorption like this. So ito yung application ng UVb. So next meeting, mag-aano na tayo, AAS na tayo. So question. Kumusta na kayo sa yung take home?
Mga sir, mga 2.5 items pa lang siguro yung nababasahan ko po. Pero wala pa akong nasusulat.
Yung paper nyo. Kasi kinukulit ako ni ma'am kumpleto. We have this special issue in Science and Engineering Journal. Kami yung in charge. For me, I don't want to submit there kasi ako nga yung isa sa in charge doon. It's just like a conflict of interest. Mukhang walang nagsasubmit we set May 15 as the extension, so we will see. So I'm hoping one of you, maybe a review paper from you will be submitted pag kinulit niya ako ulit. Good thing wala kami meeting lately sa PAASE. So
hanap muna ng topic, sir. Yun yung pinakamahirap
we only
for
have
me.
1 month, right? By June, is it June 9? Tapos na yung SEM. Although dito, yung SEM namin matatapos na next week and in 2 weeks yung sa isang school. So, by the time, May pasok ba next week during election? Wala pang memo?
So parang May 9 lang po yung walang pasok.
That is a
Same,
Monday.
sir, same.
Monday po.
Mm.
May nabasa ata ako, I don't know if it's Metro Manila, yung
Sir, yung ano po
public
ata
school?
yun? Public school po. Parang elementary high school po ata walang pasok. 1 week.
Mhm. Sa Metro Manila lang yun. But question. Tanong ko lang sa mga undergrad nyo,